So we're now looking at polynomial functions, and we're going to be graphing polynomial functions. And later then we'll get into rational functions and graphing those. So this course has a lot of tools to help us to graph. So first of all, we need to know and recognize what a polynomial function looks like. So definition in front of us states that a polynomial function in one variable is a function of the form. In one variable, okay, I had to reread that, is in the form of f of x equals a sub n, so that little subscript of n, x raised to the nth power, plus a sub n minus 1, x raised to the n minus 1 power, plus dot, dot, dot. So going in that form of decreasing in our exponent, a sub 2 x squared plus a sub 1 times x plus a sub 0. So this a sub n minus 1, dot, 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 a sub 1, a sub 0, these are all constants. And we call those the coefficients of our polynomial. The exponent n has to be greater than or equal to 0, and it has to be a whole number, or as an integer that's greater than or equal to 0. Same thing. And x is a variable. Okay. So if a sub n isn't 0, it is called the leading coefficient. And n is the degree of our polynomial. Okay, so you're going to look at your polynomial, you're going to look at your highest exponent. That is going to be the degree of the polynomial, and the coefficient, the number in front of that variable raised to that highest power, is called our leading coefficient. And those are two things that are going to be really helpful for us when we start to go graph, recognizing what the degree is and what the leading coefficient is. The domain of a polynomial function, well, there's no trouble spots. And so the domain is going to be all real numbers. So we can write that also in interval notation, negative infinity to infinity. The leading term is a sub n times x raised to the nth, and the term a sub 0, this is called the constant term. Okay, so this looks maybe confusing on all the variables and everything, but it really isn't too bad. The polynomial is in standard form if the terms are listed in descending order of power. And the last piece says that the graph of a polynomial is smooth, unbroken curve. So smooth, that means that the graph does not have any sharp corners at a turning point. Okay, so first example, we're going to have these functions in front of us, and we want to determine which of the following are polynomial functions. For those that are, state the degree, and for those that are not, state why not. Write each polynomial function in standard form, and then identify the leading term and the constant term. Okay, so first example, we have f of x is equal to 3x squared plus 5x minus 10. So thumbs up if you think that's a a polynomial, thumbs down if you don't think that's a polynomial. Okay, I should have some emotional or motion emoji things, I think. Or put in the chat yes or no what the degree is. Okay, so looking at this, we had 3x squared plus 5x minus 10, descending order of powers. If I look at my exponent, the exponent on that first term is 2 and 1 in the middle term. So it follows by definition that those are integer positive exponents. And it's in descending order of powers. And so this is already in standard form. The leading term, that would be 3x squared. The degree, well, that is equal to the exponent of that, which is 2. And the constant, in our case, is negative 10. So carry the sign with the constant or the coefficient. So looking at B, h of x is equal to 3x to the 2/3 minus 5. Polynomial or not a polynomial? Okay, so h of x equals 3x to the 2/3 minus 5. In this case, this is not a polynomial. And the reason is our exponent is not an integer that is positive. And this is because the exponent is is 2/3. Looking at C, f of x equals 2x raised to the negative third power plus 3x minus 8. Again, this actually is not a polynomial. And in this case, again, it has to do with the exponent, excuse me, and the exponent is negative 3. Okay, so that exponent wasn't greater than or equal to 0. Part D, g of x equals negative 5. So this actually is a polynomial. And the degree, well, notice there's no variable there. So the degree, if there's no variable, is 0. And recall that if you had x to the 0 power, x can't be 0 though. If you had x raised to the 0 power, this is 1. And so we can think of this, if you wanted to, as negative 5 times x to the 0 power. And so our degree is 0. Well, there's only one term, and so the leading term is the same as our constant term, which is negative 5. So leading term and constant is negative 5. Lowercase g of x, our function, which is 3s, And this, there's an error in here, because if this was a function in terms of s, then it really shouldn't say g of x, it should say g of s. So I'm going to rewrite it as 3s all times 2s squared minus 1. Well, it's not quite in standard form. Let's distribute that 3s inside the parentheses. And so if we do that, 3s times 2s squared is 6s cubed, and 3s times -1 give us minus 3s. So it's now in standard form, and it is a polynomial. It is in standard form, descending order of powers. Our degree is the highest exponent, so that is 3. The leading term is 6s cubed. The constant, notice there's no term without a variable. So the constant we can say is 0. Okay, so hopefully you can look at an equation and tell if you're looking at a function or not. Not a function, sorry. You should be able to look at a equation and see if it's a function or not, but you should be able to tell if it's also a polynomial or not. Okay, so let me see if there's any questions and then we'll move on. So there's just one question about the exponent in B. And so it was, because of that exponent, if we have anything in that form, well, if we have any exponent in a rational form as a fraction, that's not a whole number or integer greater than 0. Because remember, we can write whole numbers or integers in rational form, like 5 could be 5 over 1. But that would be okay. But if we have a rational number that can't be written as a positive integer, like 2/3, then that is considered to be not a function, not a polynomial. Okay, so looking at the following, a power function of degree n is a monomial. So remember, monomial was a term that just has one term. So a monomial function in the form of, let's see, f of x equals ax raised to the nth power. So where a is a real number, a can't be 0, or then we wouldn't have that. And n, the power is greater than 0, is an integer. So notice that we could also define a polynomial as a sum of these power functions. So looking at the following, we're going to look at the following graphs, and we're not going to pull out a graphing utility for each graph, and then answer the questions below. Okay, so looking at the following, we have 3 functions. We have y equals x squared, y equals x to the 4th, and y equals x to the 6th on the curves below. So notice they all pretty much look like a parabola, but some are flattening a little more down there by that vertex, kind of making it constant. If your exponent is higher, then basically what's happening is when you're plugging in your value of x and you're raising it to a higher exponent, that y value is going to get larger faster. And so I can see here that x to the 6th, that's a monomial function to the highest power. And so that's the one that's going to have to be the steepest. And so that's going to be this one. If we graphed x to the 4th, is going to be the next steepest one, because that's the next highest power. And then we have x squared. So this one is going to be the one in the long run growing at the slowest rate. Y goes slower, faster. Same kind of idea when we would graph x cubed, x to the fifth, and x to the seventh. The higher power, as x goes off to infinity, the faster our function is going to be growing. And so if we look at this x to the seventh, the one that is getting steeper faster. So that would be this dotted one. X to the fifth is going to be the next steepest. And then the x cubed is growing at a slower rate. So first graph, notice that all of our exponents were even. The second graph, notice that all of our exponents were odd. Notice that they have very similar shapes. So question asks, compare the graphs of the even functions. Do they share the same shape? And that looks like they do. Do they share any points? Yeah, they would. What about 0, 0? We can see that they also have other points that they share in common. So what about positive 1? If we plug in 1 there, raising 1 to and squaring it is the same as 1 to the 4th or 1 to the 6th. So the 0.11 would be the same. Negative 1, raising it to an even power is positive 1. So let's say we didn't know, we just, how could we show that those are points that are in common? Well, we could solve it. We have 3 separate equations, but we could solve it. So like if y is equal to x squared, and we have y is equal to x to the 4th. We wanted to see when is x squared equal to x to the 4th. Well, let's set this equal to 0. So let's subtract x squared on both sides. So that would give us x to the 4th minus x squared equals 0. Looking at this, I notice I can factor this. So if we pull down x squared from both of those terms, we will get x squared times the quantity x squared minus 1 equals 0. I noticed x squared minus 1 can be factored as x minus 1, x plus 1 equals 0. And so now setting each piece equal to 0, we're looking at when is x squared equal to 0, when is x minus 1 equal to 0, and x plus 1 equal to 0. So at 0, 1, and negative 1. So anytime I set those 2 equations together, those are going to be the same points I get back. Notice if I had done x squared and x to the 6th, let me just do that one to show you what's going to happen. So again, we can get everything to one side and we can factor out what they have in common. So rewriting it, I can rewrite it as x to the 6 minus x squared equals 0. Factor out an x squared here. We get x to the 4th minus 1 equals 0. We have a difference of squares. This is x squared minus 1, x squared plus 1 equals 0. Well, x squared minus 1 is a difference of squares again. So x minus 1, x plus 1. And x squared plus 1 equals 0. So again, setting each factor equal to 0, x squared equals 0 when x is 0, x minus 1 equals 0 when x is 1, x plus 1 equals 0 when x is negative 1. Only different factor that we have in this case is this x squared plus 1. But when that one is equal to 0, notice we can use that square root property. And so if we subtracted 1 on both sides of our equation and took the square root, well, the square root of a negative number, that is an imaginary number, and we get back plus or minus I. And so since that is imaginary, there's no point on the real number system where they share in common, other than that 0, 1, and negative 1 that we had talked about over here. What is the domain of an even powered function? If we look at this, the domain we talked about for a polynomial is all real numbers, and that doesn't change. So this is negative infinity to infinity. The range, so range of the y values that we're hitting. So notice that we're hitting 0 all the way up to infinity. And we're including 0, so we're going to put a bracket there. What happens to the graph in? The exponent increases to plus or minus infinity versus x approaches 0. So what happens to the graph as n increases to plus or minus infinity? Well, notice that as we're going off to positive infinity, our x value, our y values in each case are shooting upwards and going to positive infinity. Okay, so we're going to write this a little way. I'm just going to get you familiar with it. So as x goes to positive infinity, we're going to write this as LIM, the limit, as x approaches infinity of f of x. So because it's not going to one particular number, it's shooting off to positive infinity. This is going to go to positive infinity. Okay, so looking at now the graph that the exponent was odd. So comparing the graphs of the odd functions, do they share the same shape? And again, they look like the same shape, so yes. Do they share any of the same points? And so we could do it the same way that we did before. I can see that it's going to be 0, 1, and negative 1. So let's just prove it at least with one of them. So let's say we had x cubed equals x to the 5th. Excuse me. Get everything to one side of our equation. So let's subtract x cubed. So we got x to the 5th minus x cubed equals 0. Let's factor out an x cubed. So we have x squared minus 1 equals 0. X squared minus 1 again factors as x minus 1, x plus 1 equals 0. X cubed equals 0 when x is 0. X minus 1 is 0 when x is 1. And x plus 1 is 0 when x is negative 1. Okay, so we showed it algebraically. And so, at least in one case, 0, 0 is going to be the same point, 1, 1, and negative 1, negative 1. Are they symmetric with a y-axis, x-axis, or origin? So looking at this, if we folded our paper in order for it to be a mirror image, it has to be folded in force. And so this would be with the origin. And I forgot to answer that piece with even. I put the star in the wrong spot. Are they symmetrical with the y-axis, x-axis, or origin? So notice if we flip the paper across the y-axis, it would be a mirror image. And so this would be yes, the even function is symmetrical to the y-axis. The domain, there's no trouble spots in our function, negative infinity to infinity. The range of an odd power function, well, the range of an odd power function, we're hitting all of our y values. So all real numbers, we can write that as negative infinity to infinity. And then what is happening in the graph is x goes to positive and negative infinity versus x goes to 0. I didn't finish that last piece up and above. As the limit as x goes to positive infinity, it shot up and went to positive infinity, but the limit, or as we approach, and this is just saying as x approaches the value, negative infinity of f of x of our even function, notice that it's shooting upwards and going to positive infinity. But if we're talking about our odd function, as we're going off to positive infinity, notice our graph also is shooting off to positive infinity. So a way to write this again, limit LIM as x goes off to positive infinity of our function f of x, this is going to go to positive infinity. But if we're looking at what's happening as x goes off to negative infinity, notice that this is shooting downwards. This is going to negative infinity. Okay, so I just used the words limit in there, or LIM, x with an arrow heading to infinity or negative infinity, as expressing what we were saying and looking at. And that I'm just trying to get you a little bit familiar when you get into calculus. So we would be looking at the end behaviors, and this is how we would write it. Okay, so we learned how to graph using transformations in the last chapter, or actually no, it was a couple of chapters ago, in 3.5. So we can use the methods along with what we've just learned about the power function to graph the polynomial function. Y equals either x to the fourth or y equals x to the fifth. So think about part A. Use just in words to describe the graph of the function below as a transformation of the power function, y equals x to the fourth or x to the fifth. So what are you going to do to the graph of x to the fourth to graph negative 2, parentheses x plus 1 raised to the fourth power? So think about it, write down what transformations would you do to get that graph. Okay, so let's think about it. Let's look inside the parentheses, that x plus 1. So that plus 1, that's a horizontal shift when it's inside the parentheses like that. And it's the opposite of what we were thinking it would do. So, excuse me again, this one is shifting our function to the left 1 unit. So So to the left 1 unit. This negative, I'll think of it as that's like a negative times x to the 4th. So a negative that is changing my y value. And so changing my y value is going to be a reflection across the x-axis. And that 2 is a vertical shift. Or vertical stretch. So let's think about it with the graphs. So let's look at what would be on y equals x to the 4th. We know that there was 3 points, right? That was always on those 0, 0, 1, 1, and negative 1, 1. And let's see what's happening to get the point on our function with the transformations. Well, we're going to affect our x value by shifting it to the left 1, so we have to subtract 1 to it. And then our y value, we're multiplying that by a negative 2. So if we look at our point 0, 0, and we plug it in here, 0 for x and 0 for y, well, 0 minus 1, that's going to become negative 1. And negative 2 times 0 is 0. And so we have a new point, negative 1, 0. If we look at another point, so 1, 1, and we apply that formula, well, 1 minus 1, that gives me 0. And 0 times, I'm sorry, and 1 times negative 2, that's negative 2. So we have a point at 0, negative 2. And when we plug in negative 1, 1, well, if we look at this now, when we plug in negative 1 and we subtract 1 from it, we get negative 2. And we plug in positive 1 and multiply it by negative 2, we get negative 2 times 1 is negative 2. So we have a point at negative 2, negative 2. Okay, so we have this graph in here. So same idea. We want to look at g of x now, which is 1/2 times x minus 2. That x minus 2 is raised to the 5th, and then outside plus 1. So the minus 2 inside the parentheses, this is shifting it to the right 2 units. So that's affecting my x value of my new point. And I would subtract 2 from my x value. The 1/2, it's making it so it's growing at a slower rate. So it is compressing it vertically, because how our book had said it. And we're going to get 1/2 times our y value. Then we have this +1 up here. And so this is a vertical shift up 1 unit. Well, vertically, right, we're affecting our y value. So we're going to add 1 in here. So +1. So if we think of our 3 points, we can see what they are. We know the general shape of what this is going to look like from our previous examples. And so 0 minus 2 gives me -2. Plugging in 0 for y, 1/2 times 0 is 0 plus 1 is 1. My point that was 1, 1, that was on my graph of x to the 5th. Plugging in 1 for x, 1 minus 2 is -1 for my x-intercept value. Plugging in 1 for y, so 1/2 times y is 1/2 plus 1. So that's 1.5. And the other point that was on there was -1, -1. So plugging in -1 for my x value, -1 minus 2 is -3. And plugging in -1 for my y value, I get -1/2 plus 1. So that's just 1/2. So plotting our points, we have one at -2, 1. We have one at -1, 1.5. And we have one at -3, 0.5. And so this is going to come up and slowly rise. I'm just trying to think to myself. We're just going to do it. We could get a little more accurate, right, by looking at our x-intercepts and our y-intercept. G of 0 when x is 0 is going to give me my my y-intercept. And so if I did that, that would have been 1/2 0 minus 2 to the 5th plus 1. -2 to the 5th, though, this is what's getting me. -2 to the 5th, that's -32. And so this is actually going to be really steep. So -2 to the 5th again is -32. Just making sure I'm right. -32 divided by 2, that's -16 plus 1. So that's actually -15. So something's wrong with my graph. So I'm getting -32 or -15. So that's way down here, which just doesn't make sense to me. So I'm thinking I'm doing something wrong. Unless it's coming back up around, because that should be shooting off to positive infinity as we go to positive infinity. Okay, I see my error. That -2 inside the parentheses, that was shifting, like I said, to the right. But when I wrote it over here, I put a -2. So this should have been a +2. So that actually affects all my x values of the points that I found. My y value should be staying the same. So if I add 2 to 0, this would have been a positive 2 here. In this case, when I put 1 plus 2, this should have been positive 3. And then when I plug in negative 1 for x, negative 1 plus 2, that gives me 1. Okay, so we have the point at 2, 1, 3, 1.5, and 1.1, and then 0.5, and then down here. Okay, so this definitely looks like the shape of the graph I would get. Okay, so this was more, I think, kind of a review of our transformation of functions, which is something that you guys will see on the test next week. And probably this weekend on the end of the chapter, my math lab test. So we see if there's questions on that. Okay, so let's look at a polynomial function and what's happening when it's either crossing or touching the x-axis. Here it says the graph to the right shows a polynomial function with 4 x-intercepts. At the x-intercept, the graph must either cross the x-axis or touch the x-axis. Consequently, between consecutive x-intercepts, the graph is either above the x-axis or below the x-axis. So if a polynomial function f is factored completely, it is easy to locate those x-intercepts to the graph by solving the equation f of x equals 0 using the I'm not sure what they want there. I think they want the 0 property. Okay, so 0 property. So for example, let's say we have a function that's already factored for us. And the factors is x minus 1 all times x plus 5 raised to the second power. We can see that the zeros of this functions are x equals 1 and x equals negative 5. Based on this, the following statements are equivalent, where R is a point that crosses or touches the x-axis. So we say that R is a 0 of our polynomial. R is a intercept of the graph. X-intercept of the graph of f. We can write the factor as x minus r is a factor of f, and r is a real solution to the equation f of x. Okay, so those are the values that give us a 0, like 1 and negative 5. These are all equivalent statements, are all things that hold true. So the real zeros of a polynomial find the zeros of this function. Okay. It doesn't look like they stated it, so let me just do this. Oh, nope, they do. So we can factor this. This one's easy to factor. There are two numbers that multiply to negative 3 and add to positive 2. And so we can factor this as x plus 3 and then x minus 1. And so the zeros are x equals -3 and x equals 1. If we look at this, it's already factored for us. 5 is never equal to 0. X plus 1 is 0 and x is -1. And x minus 2 is 0 when x equals 2. Notice that we have some exponents on those factors. And so if we have a factor that has an even exponent, we say that that has even multiplicity. And if it has an odd, it has odd multiplicity. And then we'll talk about multiplicity in a second. But this x equals -1, this is a multiplicity. That factor occurs twice. So this is a multiplicity of 2. Looking at f of x in part B, x minus 2 cubed, that has 3 factors of x minus 2. So we would say x equals 2 has a multiplicity of the exponent, which is 3 in this case, of 3. So multiplicity, actually, looking at it, we'll see that if it's odd, it's going to cross our x-axis. If our multiplicity of our function of a 0 or factor is even, then it's going to just touch the x-axis. So it says, find the degree polynomial of a degree 3 whose zeros are -4, -2, and 3. And then using graphing utility to verify your results. Okay, so we're using the fact, and we're going to use this a lot in this chapter. And we're going to need to learn how to, or recall how to do long division of polynomials or synthetic division. So we're going to get to really high degrees of polynomials and be able to use some tools to help us find the zeros. And a lot of times we want to rewrite these as factors. And so if x minus 4 is a 0, you can think of it as this, x equals -4 is the 0. The factor then, if we added 4 to both sides, x plus 4 equals 0. So x plus 4 is a factor. If x equals -2, that's a 0. Think of it, you have to add 2 to both sides. X plus 2 equals 0. That's going to be our factor. And x equals 3, well, we would subtract 3 on both sides to get that set to 0. So x minus 3 in our case is a factor. We could technically put any number out front, any coefficient, and that would keep those still as the zeros of the polynomial, and it wouldn't change my degree. It looks like it wants me to expand this out, and so you would do that by distributing x plus 4 times x plus 2. So in that case, we would get x squared. I'm just curious about my middle term. This is going to be a 2x plus a 4x. So that gives me, middle term is plus 6x. And 4 times 2, that would give me a plus 8. All times x minus 3. So again, we got to distribute. So x squared times x, that gives me x cubed. X squared times -3, that's minus 3x squared. 6x times x, so that gives me 6x squared. 6x times -3 is -18x. 8 times x, so 8x. And 8 times -3 is minus 24. So standard form descending order of powers, and let's combine like terms. So x cubed is the largest term with the largest exponent. We have a -3x squared plus a 6x squared, so that is plus a 3x squared. We have a -18x plus an 8x, so that's minus 10x. and then minus 24. Okay, so we just found a polynomial function that has the zeros -4, -2, and 3 that has a degree of 3. So let me just pull that up really quick since I have the program Desmos up and show it, and then we'll take a break. Okay, so I put our function into Desmos and graphed it. And so notice that we do have our x-intercepts at -4, -2, and +3. And that's what we were given. And those are what we had said. Those are the intercepts. But recall, I told you that we could multiply this function by any value of x, maybe. And that would not affect my intercepts. Any value, not any value of x, any constant. So for instance, if we multiplied this by -3 out front, that doesn't change where my x-intercepts are. If I multiplied this by 100 out front, that's not changing my intercepts. So I could really, there's an infinite number of functions that have those intercepts, because I could write any real number outside of the polynomial we just found, and that would still give me the same intercepts. Let's take a break, and then we'll come back and work more on this section. Okay, so let's look at the following, and this states that if we say x, plus, or actually I think it's minus in our book, or what they're going to say, x minus r raised to the m power is a factor of the polynomial f, and this x minus r raised to the m plus 1 power is not a factor of f. Then r is a real zero of a multiplicity m of f. Okay, so basically it's saying you're going to look at the maximum number of factors of, in this case, x minus r. We're not going to have one additional one. And so, for instance, if we had x minus 2 to the cubed, we couldn't have another factor out here, x minus 2, because technically there's 4 factors. This is the same thing as x minus 2 to the 4th. So in this case, x equals 2, if I had this as y equals, or f of x equals 2 is a 0 with multiplicity 4. Okay, so in other words, if r is a real zero of a polynomial and the exponent of the factor that produced the root is m, then we say that r has a multiplicity of m. Okay, so notice in 3b, well, I'm going to have to go back up because I don't remember what 3b is. The real 0 is -1 was produced by the factor x plus 1 quantity squared, and the real 0, 2 was produced by the factor x minus 2 cubed. Because the exponents of these terms are 2 and 3, respectively, we say that x equals -1 has multiplicity 2, and that the real 0, 2 has a multiplicity of 3. So let's just go back up there. So 3b, and I had stated this up here already. So x minus 1 is set x plus 1 equal to 0, and 2 is our exponent, so that was multiplicity 2. X minus 2 cubed, 3 is our exponent, so it's multiplicity of 3, and x minus 2 is 0 and x equals 2. So turning points and multiplicity. Oh, sorry. I would have stated now about our intercepts, but I guess that waits. So example 5, for the polynomial function f of x equals negative x cubed all times x minus 3, that quantity x minus 3 is squared, and all times x plus 2. So with this polynomial f of x, we want to find the x and the y-intercepts. Okay, let's do the y-intercept first, because that's probably the easiest one. So actually, no, it's not. But let's do it because I said. So y-intercept, this is where we let x equal 0. So a way we could write that in function notation, we're looking at f of 0, right? And wherever we see an x in our function, we're going to replace it with 0. So first we're going to go in, put parentheses wherever we see an x, and then put 0 wherever we have our parentheses. So we have negative parentheses cubed, parentheses, inside the parentheses is a parentheses minus 3. That is quantity squared, parentheses, parentheses plus 2. Okay. So looking at this, 0 cubed, well, that thing out front is 0. And so it really doesn't matter what the rest is, because negative 3 squared, that's 9. And 0 plus 2 is 2. But 0 times anything is 0. So we have a y-intercept at 0. The x-intercepts are not bad because it's already in factored form. So let's list the x-intercepts and state the multiplicity of the 0. So x minus 3 is equal to 0 when x is equal to 3. And this has a multiplicity of 2. X plus 2 is equal to 0 when x is negative 2. Usually we don't say multiplicity 1. But I'm going to put it anyways. And then we also have negative x quantity cubed. So x cubed is equal to 0 when x is 0. And the multiplicity on this one is 3. Okay. So use the graphing utility to graph the function for each x-intercept, determine whether it is odd or even multiplicity. Well, we already stated the multiplicity, and so x equals 3. This is an even multiplicity. X equals negative 2 had multiplicity 1, so this is odd. X equals 0 had multiplicity 3, so this is also odd. So I'm going to go and we'll plug this in so we can see what the graph looks like. And it's going to talk to us about what's going on at those intercepts. And we're going to see if we notice anything based off of even or odd. Okay, so we have our function in front of us. And looking at our multiplicity, look at that x equals negative 2. The graph crosses the x-axis there. At x equals 0, the graph also crosses the x-axis there. And at x equals 3, it just touches the x-axis and turns back around in the same direction as it was coming in on. And so we'll see that when we add an odd multiplicity of a 0, that's going to make it cross the x-axis. And when we have an even multiplicity, we'll see that our graphs is always going to change. It's just going to touch the x-intercept there and change directions and go back from where it was coming from originally. Okay. So for each x-intercept, determine whether even or not, and we just did that. So same sort of idea, graphing a polynomial using its x-intercepts. We have f of x equals x minus 2 quantity squared, all times x plus 1. We want to find the intercepts, x and y intercepts. So we have x-intercepts. That's when our function is equal to 0. And so we have x-intercept at x equals positive 2 with multiplicity 2. And x plus 1, so x equals negative 1, which multiplicity 1. So you use the x-intercepts to find the intervals on which the graph is above the x-axis and the intervals on which the graph is below the x-axis. So if we look at this, let's put this on our number line, and we have negative 1 and 2. So we want to see what's going on. Is our graph above or below the x-axis on the left or right of these intercepts? And so we want to test values. So we're kind of doing this when we had quadratic inequalities last week. So choose a value that is less than negative 1. And so if I chose x equals negative 2, we want to know if we plug in negative 2 wherever we see an x, are we going to get back a positive or negative number? So if we plug in negative 2 here, I get negative 2 minus 2, which is negative 4, and negative 4 squared is 16. And then I have negative 2 plus 1. So negative 2 plus 1 is negative 1. I really just care if it's negative or positive. I guess it could help me graph later. This is negative 16. So this will be x from negative 2. Sorry. Let's do it this way. How about negative infinity to negative 1? We know that this is below the x-axis. Or another way to state that, right, is f of x, our y value, is less than 0. So let's see what's happening in between x equals negative 1 and 2. So choose a value that falls in there. And so if we plug in 0, so if we go back in and look at f of 0, you know, want to know if it's positive or negative. And so we have negative 2 quantity squared, which is positive 4. And then 0 plus 1, so that's 1. So this is a positive number. So I know that between the x values of negative 1 and 2, the graph falls above the x-axis. So negative 1, 2, our graph is above the x-axis. So our y value, f of x, is greater than 0. So one more value, something bigger than 2. So how about x equals 3? So if we go back in here and we plug in 3 wherever we see an x, we get 3 minus 2, which is 1. 1 quantity squared is 1. And then 3 plus 1 is 4. So this is also positive. And so that is also above the x-axis. So union 2 to infinity. Okay, so above the x-axis and below the x-axis, we found our values. So locate other points on the graph and connect all the points plotted with a smooth, continuous curve. Okay, so doing this again, we have our x-intercepts, so let's plot those. They were -1 and +2. We saw that it is below the x-axis from -infinity to -1. Below the x-axis. We actually had a point there, right? We had plugged in -2, and we got that was -16. So this is way below the x-axis. We could get a little bit more accurate. So we're just going to say way down here. We then saw that it fell above the x-axis between 0 and, between -1 and 2. And we plugged in 0, and we saw that at 0, we got back a 0.4. So we have a point here at 0.4. We're not sure where this is going to be changing direction, and we're not going to really know that until we either use a technology or until you get into calculus. And then you'll get the tools that you'll be able to find those max and min points. So we could technically plot a couple more points in here. For instance, if we plugged in 1, let's see what we would get back. Let's get our function again. So we have 1 minus 2, which is -1. -1 squared is 1. And then we have this 1 plus 1, so times 2. So this is equal to 2. So x equals 1, we have 2. And then we saw that at x equals 3, that it was again above the x-axis for values greater than 2. And at 3, we also got 4. So we have some general sketch of what's going on, but we don't have it totally. Okay. So let me pull and just show you that what we got was similar to what Desmos would get. So this was, okay. So this was x minus 2 squared. Rid of this other piece. All times x plus 1. And that's similar to what we had gotten. Let's see what we have next. Okay, so use the graph of 5b record below what the difference is in the even and odd multiplicities. So numerically, the sign of f of x let me just read what it's saying again. So if r is a real 0, even multiplicity, then the signs of f of x are the same from one side to the other side of r. Graphically, the graph of f touches the x-axis at r. So we saw at x equals 2, it was even multiplicity. Each side we looked at were positive. And it just touched there. So if R is a real zero of odd multiplicity, numerically, the signs of f of x are opposite from one side to the other of R. Graphically, the graph of f crosses the x-axis at R if we have odd multiplicity. Okay, so looking at turning points on a graph. So the number of turning points in the graph of a polynomial has to do with the degree of the polynomial. And so let's look at the following, what it states. So turning point theorem, a turning point on a graph is a point where the function changes from increasing to decreasing or vice versa. So increasing to decreasing, so like a max, or from decreasing to increasing. So these are turning points on our graph. These points are local maximum or local minimums of our function. And we talked about that before and finding those by looking at a graph. An example of a turning point is the vertex of a parabola, the parabola y equals x squared. The degree of this polynomial is, remember, it's the highest exponent. So this would be 2. And there are, well, again, y equals x squared. If we look at how many turning points are in this, notice that there's just one turning point. So if a polynomial function of degree n, then the graph of f has at most one less turning point. So n minus 1 turning points. So if the graph of a polynomial function f has n minus 1 turning points, then the degree of f has to be at least one more than that. So would have to be at least n. So state the degree and number of turning points for the following. So if we multiplied this out, and I'm not going to do that, so you should be able to look at this and be able to figure it out without. If you multiply this out, then we should have an x squared. So our degree is x squared. Or I'm sorry, we'd have an x squared term, so our degree is 2. And number of turning points is going to have just one turning point. Okay, so looking at the end behaviors of our graph of a function, it really has to do with that leading term. So that coefficient and that degree, that term with the degree of our polynomial. So the end behavior of the graph of a polynomial function, and we stated what a polynomial function would look like. This f of x equals ax to the n plus a sub n minus 1, x to the n minus 1, dot, dot, dot. A sub 1 x plus a sub 0, where a sub n can't be 0, is the same as the graph of the power function y equals a sub n times x raised to the nth power. In calculus, we'd say the value of f becomes larger or smaller as x becomes larger or smaller. And in the case of f of x equals x cubed, we'd write this as f of x with an arrow. So that's the saying our y value goes to negative infinity. So an arrow to negative infinity as x approaches, so an arrow negative infinity. And we would say that f of x, as x goes to infinity, as x goes to infinity. Right, so as x goes to negative infinity, f of x, our y value, shoots to negative infinity. As x goes to positive infinity, f of x, our y value, goes to positive infinity. In addition, another notation involves using limits to convey this idea, and that's how I kind of expressed it with you guys. That limit, x arrow infinity, underneath that lim, f of x equals infinity, or the limit as x arrow negative infinity, f of x equals negative infinity. So find the real zeros of a polynomial and state the end behaviors for the polynomial. List the zeros and the multiplicity. Okay, so let's think about it. If we distributed this all out, what would our leading term be? And our leading term here, I noticed that none of these have a coefficient other than 1 in front of my x, and there's just a coefficient of 1 outside of all the parentheses. So my leading coefficient is going to be positive 1, x raised to the, well, x times x, that's an x squared term, and x squared times, well, this is an x squared here because I'm squaring it. So x squared times x squared is an x to the 4th term, adding our exponents. And an x to the 4th term times this last factor with x in it would be x to the 5th term. And so I can see then that my leading term is going to be x to the 5th. So my end behaviors are based off of x to the 5th. And so if I look at this, the limit as x approaches negative infinity of f of x, if I plug in negative numbers, raise it to the 5th power, it's going to be shooting downwards. It's going to be going to negative infinity. If I look at the limit as x approaches positive infinity of f of x, if I plug in positive numbers to x to the 5th, it's going to be positive. It's just going to get larger and larger. So this is going to positive infinity. My zeros, well, set each factor equal to 0 and solve for x. So x plus 5 is 0 and x is negative 5. Multiplicity, well, there's no exponent, so it's just 1. X plus 1 is 0 and x is negative 1. And multiplicity is 1. X minus 2 is equal to 0 and x is 2. We have an exponent here, that's multiplicity 2. And x minus 4 is equal to 0 and x is 4, multiplicity 1. Okay, so we found the zeros and we talked about what was happening with the end behavior. So we can kind of figure out what the graph is going to look like, the general shape, right? Because of where our zeros are. So let's first plot those zeros on the number line, not on our number line, on the x-axis. And so we have one at negative 5. We have one at negative 1. We have one at positive 2. And at 4. So our end behavior we know is shooting downwards. So this is shooting downwards in here. So now I can determine, is this going to cross or just touch the x-axis? Well, it has to do is my multiplicity odd or even. So this is an odd multiplicity that tells me it has to cross it. So I know somewhere in here, I don't know where, and I won't know until I take in calculus or I plug this into a graphing calculator of some sort, that this is going to change direction and come back down to this negative 1 because that's an intercept. Again, I would look at the multiplicity to see if it's touching or crossing. And it tells me it's crossing because it's odd. Somewhere it's going to change direction. It's going to come back up to this 2. The thing is at x equals 2, we have an even multiplicity. So this is actually going to change back direction to where it was coming from before. Somewhere it's going to change direction in here. I don't know where. And it's going to hit x equals 4. And I know that it crosses at x equals 4 because my multiplicity is odd. And my end behavior I know should be shooting upwards, which this is, as x goes to positive infinity. So again, we can get a little bit more accurate if we start plotting a little more points in between to see how far it might dip down or come up. But we won't be able to find that exact position where it's changing direction or what that actual maximum value is or minimum value is at those turning points. And that's something you're just going to have to wait for. And you'll get to see that in calculus. Let's see what the next problem is, and we'll see if we have enough time. Okay. Yeah, let's just do this really quickly. So write a polynomial function whose graph is shown. Use the smallest degree possible and verify your results with a graphing calculator. A couple of things we know. We know that right here, we have a factor because the 0 is x equals -3. We have a factor of x plus 3. We want the smallest degree. I know it's crossing, so it has to be an odd multiplicity. Well, the smallest degree would be 1 then. I know that I have a factor here at x equals, x equals -1, so my factor is x plus 1. It's just touching here, and so I know my multiplicity has to be even, and so smallest power of an even multiplicity would be 2. One more multiplicity, or one more intercept. Well, x equals 2, so x minus 2 would be the factor. And it's crossing, so it had multiplicity 1. I don't know what this number is out here, if it's other than 1, but I can actually figure that out because I see a point, just locate a point on the graph. And I see a point right here at, oops, that's not a point. I see a point right here at 0, -3. So we can go in there, we can plug in what x is and what y is, and at this point, and solve for a. So I know when y is -3, this is equal to a. All times, well, if I plug in 0 wherever I see an x in here, I get 3 for the first factor. 0 plus 1 is 1, 1 squared is 1, and then 3 minus 2, that gives me, oops, I'm supposed to be plugging in -3, not 3. Oh no, I was right. I was right. Plugging in 0. Okay, so that was 3. Trying to erase. 0 plus 1, so that's 1. 0 minus 2, that's -2. So I have -3 equals 3 times 1 times -2 is -6a. Solve for a, divide both sides by -6. We get a is 1/2. And so we've just found our polynomial function with the smallest degree for that graph. So that is 5.1.